Okay, welcome back. We are looking at the top of page 102, and this is the continuation of example 1 from page 101, asking us to do an additional calculation here. And just so you don't have to keep flipping pages back and forth, let me remind you of the matrix that we already found on the previous page. So we started with linear transformation and discovered that its matrix relative to the standard basis looked like this, 1, 8, 2, 1. All right, so we've got that in front of us. And here's what they're asking us to do. Okay, they'd like us to use theorem 2.23 as a guide. Okay, we'll write that down in a minute. We'd like to find a diagonal matrix D and an invertible matrix Q such that D is equal to Q inverse AQ. Okay, what this essentially is it's a way of factoring the diagonal matrix D in terms of the matrix A that we already have. It's going to turn out that this factorization is very useful for doing matrix calculations in the next section. Okay, so let's see if we can unpack this together here. Right? So first, let's remind ourselves of what theorem 2.23 was about. It was a way of relating two matrices for the same linear transformation, matrices relative to different bases. And here's what it said, basically. Okay, that if there's a second basis beta prime for our vector space, then the matrix of T relative to beta prime is equal to Q inverse times the matrix of T relative to beta times Q. Okay, where Q is just the change of matrix, change of basis matrix. Okay, where we're going from beta prime to beta coordinates. Okay, and in the notation of our problem, this T beta is what we've decided to call A, and it's going to turn out that T relative to beta prime is going to be the diagonal matrix that we want. Okay, maybe one other comment, and that is beta prime, if you look back at part A, that was the second basis for R2 that consisted of our eigenvectors. Okay, so I'm going to remind you of that. Okay, beta prime looked like, let's see, what were our eigenvectors? 2, 1 and negative 2, 1. Okay, so if we want to confirm this equation up here, we need to do some calculations. All right, so let's do that below. So one thing that we need is we need to actually calculate the matrix Q, this change of coordinate matrix. So let's start there. Okay, and it's a change of coordinate matrix going from beta prime coordinates to beta coordinates. So if you look back at the way that works, we're going to start with the vectors in beta prime, 2, 1 and negative 2, 1. And we're going to try to write those as a linear combination of the vectors in beta, okay, which was the standard basis. Okay, so we can maybe remind ourselves that this is referring back to part A again. Beta was the standard basis for R2. Okay, so how would we write 2, 1 as a combination of the standard basis? Well, because it's the standard basis, that's not too hard to do. It's just going to be 2 times 1, 0 plus 1 times 0, 1. Kind of the same idea for negative 2, 1. We're going to get negative 2 times 1, 0 plus 1 times 0, 1. Okay, and building that change of coordinate matrix is all about looking at those coefficients. Okay, and so what we're going to get, let's write it over here to the right, is Q. That looks like 2, 1, negative 2, 1. Same process of building a change of coordinate matrix. Okay, and I want to pause here for a minute and ask you, do you notice anything special about the columns of that matrix? 2, 1 and negative 2, 1. Notice that those columns are exactly the eigenvectors. Okay, up here in beta prime. Remember, beta prime from part A was a basis that consisted of eigenvectors of our linear transformation. Okay, so we have calculated Q. Let's move on and see if we can calculate the other side of our equation here, the matrix of T relative to beta prime. See what happens there. Okay, well, the idea, again, of calculating a matrix of a linear transformation, we've just got one basis, beta prime, so we're going to take the vectors in beta prime, which are 2, 1, and negative 2, 1. Okay, and we need to calculate t of both of those vectors, so this might be a good time to remind ourselves what the formula for t was. Okay, and I'm looking back at part A and just writing down the formula that was given way at the beginning of the problem. It looked like this. T of x1, x2 looked like x1 plus 8x2 and 2x1 plus x2. All right, so help me out here. If we take t of 2, 1, we're going to plug in 2 for x1 and 1 for x2 into this formula. You can confirm my calculations and verify that this is going to be 10, 5. Okay, and then similarly plug in negative 2, 1 for x1 and x2. This time we're going to get 6, negative 3 out. And the question is, how do we write those two vectors as a combination of those same vectors in beta prime? So 2, 1 and negative 2, 1. Okay, well, notice that the 10, 5 that we have here, that's a scalar multiple of 2, 1. So all we need to do is put a 5 there and a 0 there, and we've got a true statement. And kind of a similar thing happens with 6, negative 3. That's a scalar multiple of the second vector. Negative 2, 1, we can put a negative 3 in front of that and a 0 in front of 2, 1, and we've got a true statement. Okay, so we have just demonstrated, if we read off those coefficients, that our matrix of T relative to beta prime looks like this. 5, 0, 0, negative 3. Okay, and if you look back at our work at the top of the page, this was the matrix that we called D, and we were hoping was a diagonal matrix. We've just confirmed that. We've got zeros everywhere except along the main diagonal. Okay, and pause here again. Do you notice anything special about the numbers on the diagonal here? 5 and negative 3. Those were the eigenvalues that we found in part A, the eigenvalues of this linear transformation. That's also not surprising if you think about theorem 5.1. It said that this diagonal matrix that we calculate should have the eigenvalues on the main diagonal. That was the second sentence of the theorem. Okay, and so putting it all together, here's what we have. 5, 0, 0, negative 3. And I'm looking back at the top of the page here. Okay, this is using theorem 2.23 and just literally writing out the pieces that we just calculated. Okay, and let's just label those pieces. So this first matrix is the one we were calling D. Here's Q inverse. Here's A, and here's Q. Okay, and that's exactly what we wanted to demonstrate. And in the next video, we're going to generalize this by noting the observations that we made, the fact that what's special about Q is that it has eigenvectors as its columns, and what's special about D is that it has eigenvalues on the main diagonal.